This video is probably the most intuitive derivation of E equals mc square. It's how Einstein originally derived it in 1905. Not only will we see exactly how the constant speed of light inevitably leads to the mass-energy equivalence, but we will visualize all the necessary math, step by step, from scratch. So, if you're ready to relive this historic moment, let's begin. So Einstein, where do we start? Well, Einstein says, imagine we have a radioactive atom and it has some energy in it. For the sake of simple numbers, let's say it has 10 units of energy in it. And I love simple numbers. Thank you, Einstein. Now, Einstein says, if we wait for some time, let's say it shoots 2 photons of light exactly in the opposite direction, each carrying 1 unit of energy. And I'm like, wait, why did you imagine 2 photons going in the opposite direction? Well, Einstein says, well, if you had only 1 photon, then there'll be some recoil due to momentum. And so just to make sure that the atom does not recoil, he's making sure there are 2 photons going in the exact opposite direction, ensuring that the atom stays put, it is still at rest. Okay, pretty good. So Einstein now asks, what is the new energy inside the atom? Well, if it has lost 2 units of energy, 1 unit each in each photon, then it should now have 10 minus 2, 8 units of energy in it. And Einstein says, perfect. Now, one last step Einstein says is, his friend is piloting a rocket and she's moving towards the right at a constant velocity v. Einstein now jumps into that rocket. And now he asks, from this rocket's reference frame, what now is the energy of this atom? And at this time, I ask Einstein, is this ever going to end? And Einstein says it's going to end. Okay, this is the last step, he says. All right, so from the rocket's perspective, the rocket is not moving. In fact, it feels like the atom is the one that's moving towards the left with the velocity v now. And therefore, along with that 8 units, it also has an additional kinetic energy. And so we would say, now from the rocket's perspective, the atom should have the energy of 8 plus half mv squared. And that now is the energy that we would assign to that particular atom. But now here's the question that Einstein asks. His friend has always been in the rocket, moving with the velocity v. She has been seeing the atom even before it shot the photons. So Einstein asks, what does the calculation look like from her point of view? What would be the final energy of the atom as seen by her? And at first I would say, like Einstein, she should get the same answer, right? Because eventually both you and her are in the same frame. So both of you should agree, they're looking at the same atom, so we should agree what the final energy of the atom is. And Einstein says, yes, but let's just do the calculation from her frame and let's see what we get. All right, let's do that. So from her frame, she always appears to be at rest and she sees the Einstein and the atom to be moving towards the left with speed v. And therefore, from her perspective, the initial energy of the atom was 10 plus half mv squared because it's already moving. And then she sees that atom shoot 2 photons of light, and therefore the energy of the atom now decreases by 2. So it becomes 8 plus half mv squared. And I'll tell Einstein, look, like I said, we get the exact same energy as before. She also says it's 8 plus half mv squared. You also said it's 8 plus half mv squared. Everyone is happy. Let's just what are you asking? But Einstein says, Mahesh, you forgot something. What's that? Doppler effect. Einstein reminds us that light also has wave properties. And so if we were to look at the atom when it's at rest, this is how the waves would look like. But now when that same atom is moving, look at it. Look at it. It's exactly the same atom giving out the same number of waves per second. Let's look at it together. Look at that. It's giving out the same number of waves per second. But because the atom is moving, what do we see? Well, we see that in the front of the atom, the wavelength has squeezed. And so the frequency is higher. The waves are closer. And behind the atom, the wavelength has stretched, so the frequency is lower. And therefore, if from the stationary frame, if the photons had these frequencies, then when you're looking at that atom from the moving frame, from the rocket, Einstein's friend, she wouldn't see the same frequency of the photons. In fact, she would see over here a higher frequency of the photons, which we call blue shifted. Now, it doesn't mean, Einstein says that the photon is not really blue in color. It's just called blue shifted because, and the frequency is higher, it's moving towards the blue end of the spectrum. That's what it means. And just for representation, we are showing it as blue. But she will see a higher frequency photon on this side. And on the other side, she would see a red shifted, lower frequency photon on the other side. That's what Einstein's friend would see. Okay, Einstein, but why should I care about the frequencies? Because Einstein says, remember, energy of a photon is equal to h into its frequency. Planck's equation. So energy depends on the frequency. This means if these 2 photons had the energy 1 and 1 unit, then these two photons will not have the energy 1 and 1 unit. This blue photon will have a energy higher than 1. This red-shifted photon will have energy lower than 1. We didn't account for that. Okay, so Doppler effect is interesting. All right, my first counterattack to this is, Einstein, well, since this photon will have energy more than 1 and this photon will have energy less than 1, won't it just work out that the total energy will become 2? And Einstein says, no. I mean, we'll have to actually do the math to figure this out, which we will do. But even intuitively, you can see, just from this diagram, you can kind of see over here, the wavelength is squeezed so much that the frequency is almost double in this particular animation. So if the frequency is double, this photon already has twice the amount of energy. So look, that photon already has 2 units of energy. Now this photon, redshifted photon, will have energy less than 1, sure, some energy, let's say 0.2 for the sake of numbers. And look, because this blue shifted photon already is dominating, the total energy becomes 2.2 higher than the total energy that we saw earlier from the rest frame. And this would be true, Einstein says, if we do the math for any velocities. It doesn't matter what velocity we are moving at. If you correctly look at the Doppler shifted energies, the total energy will always be more than the energy that you find from the rest frame. And of course, as we'll do the math, we'll actually figure this, we'll see this as well. Okay. So what does this mean, Einstein? Well, this means if we go back over here, we made the mistake that she would see the photons of having the same energy, 1 and 1 unit, but which is wrong. Now, if you take those same numbers, she would instead see a blue shifted photon and a red shifted photon with a total energy of 2.2. So from her frame, this atom lost 2.2 units of energy, and therefore she would claim that the final energy of this atom would be 10 minus 2.2, which is 7.8 units of energy. And therefore, from her frame, she would suggest that the energy of the atom would be 7.8 plus half mv square, moving towards the left. But wait a second, Einstein. These two energies of the atoms are supposed to be equal to each other, right? Because they are now in the same frame together, they're looking at the same atom. And Einstein says, yes, they're supposed to be equal, but how can that be equal? This equation says that 8 should be equal to 7.8, which is impossible. And Einstein says, Mahesh, remember how to approach special relativity? You don't approach it with a closed-mindedness and say it's impossible. Instead, you ask yourself, what needs to happen in order for it to be possible? Okay, all right. What needs to happen for this equation to be possible? Well, let's look at it, says Einstein. If you simplify a little bit, you get 8 minus 7.8, 0.2 on the left-hand side, plus half mv square equals half mv square. And I'm saying, Einstein, look at it. This equation is saying that the half mv square on the right-hand side should be more than the half mv square on the left-hand side by 0.2. And I'm saying the velocities has to be exactly the same because they're looking at exactly the same atom, right? The same atom, they're moving at the same speed, so the velocity must be the same. And Einstein agrees. Of course, the velocity is the same. This means there's only one possible conclusion if this equation has to be valid. That is, the mass on the right-hand side should somehow be bigger than the mass on the left-hand side. But I'm like, how can that be, Einstein? Both of these are the masses of the same atom. They're looking at the same atom. Why would they conclude the two different masses? And Einstein says, Mahesh, look carefully. This mass on the right-hand side is the mass of the atom before it shot the photons. And this mass on the left-hand side is the mass of the atom after it shot the photons. Which means this equation is saying that the atom must have lost mass because of shooting the photons. In other words, look at this. This is the history in the making, folks. This equation is staring at us and saying that the fact that the atom lost energy means it must have lost mass. That's the only possible conclusion. Whoa. And what I love about this derivation is that we didn't start with any assumption. We didn't think about its mass or anything. But the fact that Doppler effect gives you more energy in the photons from the moving frame means this is only one conclusion, that losing energy means losing mass. Whoa. But wait a second. I promised you complete intuition. So I have a question. Well, this happens due to Doppler effect, right, Einstein? Well, but Doppler effect happens in all the cases, in all the waves. So why do we only see this in light in special relativity? What Einstein replies to this is what truly blows my mind away, because there's a subtlety in the Doppler effect of all the other waves. So if you consider, for example, the waves produced by a speaker, the sound waves, the big difference is that sound waves require a medium to travel. And therefore, now if I blast off into a rocket towards the right, sure, now I will see the speaker moving towards the left. But along with that, the medium is also moving towards the left with the same speed. So there is a wind towards the left with the same speed. What happens because of that, Einstein? Well, Einstein says, now, because of the wind, the velocity of the sound towards the left gets an additional boost by the exact same amount. Because of that, it does not allow the wavelength to shrink on the left-hand side. And the velocity of the sound on the right-hand side becomes slower because it's going against the wind, and so it doesn't allow the wavelength to stretch. And therefore, if you could see sound waves now, this is what it would look like. Because of the change in the velocity in different direction, the wavelength stays put. You would see exactly the same wavelength as you would see when you are at rest. And it kind of makes sense because the speaker is still at rest relative to the medium. There is a medium to distinguish whether it's the speaker that's moving or that's me, the observer, that's moving. If there were some hypothetical sound photons, they would have exactly the same energy as look from the rest frame or as look from the rocket's frame, and therefore you would have no discrepancy. But then why does it happen for light, Einstein? Because light does not require a medium. That's the key. And therefore, because light doesn't travel in a medium, it doesn't have anything. The speed of light is the same in all reference frames. And because the speed of light does not change, therefore we see the change in the wavelength causing the change in the energies of the photon. This means it's the fact that the light travels in vacuum, and the fact that the speed of light is the same in all the reference frame is directly responsible for this effect. E equals mc squared. Can you see now? The whole energy mass equivalence comes directly from special relativity. Can you see that connection now? Oh my God. Oh, that's the reason why when you lose energy, you have to lose mass. Whoa. When this first clicked in my mind, I knew, oh my God, I had to make a video and share it with somebody. And so I hope it clicked in your mind as well. And this is the kind of intuition I like to make on this channel. So do subscribe if you're new here. But if you don't, it's fine. I will not. No hard feelings. Because now we need to figure out exactly how much mass did it lose. So how do we do that, Einstein? Well, Einstein says, let's rearrange this equation, bring that half mv squared on the other side. And if we can now write this as half times delta m times v squared equals 0.2. But what exactly is this 0.2? Well, Einstein reminds us that 0.2 is actually the difference in the photon's energy from the moving frame and from the rest frame. So this 0.2 is basically the energy of the photon in the moving frame, this 2.2 that we got over here, minus the energy of the photons in the rest frame, that is this 2 over here. This means our next step is to figure out exactly how much is the energy of the photon from the moving frame, which means we'll have to do the math for the Doppler effect. And I thought, okay, let me just look at what Einstein did. And in his paper, he didn't do any derivation because he had already derived it. And at this point, I thought, okay, this is it. I'm going to lose my intuition over here. Relativistic Doppler effect, the math is going to be so complicated. Oh no. But no, we can do the Doppler effect completely intuitively as well. Are you ready for this? Let's do that. We'll first look at the atom at rest and calculate its frequency. And the simple way is we'll look for 1 second and count how many waves it emits. All right, ready? Let's go. Okay, timer starts. 1, 2, 3, 4, 5 waves. So in 1 second, it gives out 5 waves. Therefore, its frequency is 5. Now the key question is, what is the wavelength over here? Now you might say that, hey, you know the wavelength equations, lambda is equal to c divided by f. But if you do it that way, no, the intuition will be lost. We have to do this logically, because if you do that, then you can use the same logic even for the moving atom, all right? So here's how I like to think about it. I like to concentrate on that first wave, the distance that the first wave traveled. So let's look at it one more time, only concentrating on the first wave. When we look at it, here it goes. Look at it. That first wave is traveling for 1 second. And since it's traveling at the speed of light, this means the distance that the first wave must have traveled is c. And therefore, this means that in this distance of c, there must be 5 waves. So 5 waves occupy a space of c meters, or c distance. And therefore, to calculate the wavelength, now I ask myself, how much does one wave occupy? Well, one wave will occupy c divided by phi. And look, this is how the wavelength turns out to be c divided by frequency. Does it make sense now? Or we can now say the frequency should equal to c divided by the wavelength. Now let's do the exact same thing for a moving atom. All right, now for the moving atom, because the atom is moving, in 1 second, it also has moved some distance towards the left. Now, if it's moving towards the left with some speed v, then in 1 second, the distance it would have traveled is v. And now here's the key thing. This means that these 5 waves on the front are squeezed in this small distance. How much distance is that? Can you see that is c minus v? And therefore, this time, the 5 waves occupy a space of c minus v meters. Therefore, what is the wavelength? How much does one wave occupy? It occupies c minus v divided by 5. This is the new wavelength. And therefore, what will be the new frequency? Well, the new frequency, just from this formula, is going to be c divided by the new wavelength. I'm calling this the blue shifted frequency, divided by the new wavelength. And we know the new wavelength. The new wavelength is c minus v divided by 5. That 5 is the original frequency, the frequency of the source. And if you just rearrange it, we got the blue shifted frequency. Look at that. Isn't that beautiful? And here's the way I like to do sense check. If I put that velocity to be 0, look, fb will just become f, and that makes sense. We'll go back to being over here. On the other hand, if we made v is equal to c, the denominator goes to 0, and I get fb to be infinity, which makes sense because if this was going at c, and I know we can't go at c, remember, but mathematically what's happening is that the waves will not be able to travel in front of it, and all the waves will stick together, and therefore wavelength goes to 0, frequency goes to infinity. Just think about this, and this equation makes complete sense, isn't it? But at this point, for all of this time, Einstein has been screaming from that side, saying, I forgot something. All right, so let's bring Einstein back again. Einstein, what did I forget? Einstein reminds us that we forgot time dilation. When atom is moving, its time would have slowed down. And therefore, when 1 second is up for us, 1 second is still not been up for that atom. Therefore, it would not have finished emitting 5 waves. It would have emitted less than 5 waves. So at first, it feels like, it's complicated. How do I account for that? But Einstein reminds us not to worry. For example, if the time is dilated by a factor of 2, if the time has slowed down by a factor of 2, then instead of emitting 5 waves, it would have finished emitting only 5 by 2 waves. If the time dilation factor is 3, then it would have just emitted 5 by 3 waves. In other words, if I know how much the time dilation is, how much the time has slowed down, I just need to divide it by that number and I'm done. But Einstein, how much? How do I know how much is the time dilation? And Einstein reminds us, gamma. We've done this in our previous video. We know that the time dilation factor is always gamma. And therefore, all we need to do to make a relativistic correction for this is divide that by gamma and we are done. So relativistically, the blue shifted frequency will be this number divided by gamma, and we are done. What we have right in front of us, folks, is the relativistic Doppler shifted frequency. In special relativity, we did Doppler effect intuitively, logically. Isn't that amazing? Oh my goodness. All right. But remember, it's not the frequency that we're interested in, it's the energy that we are interested in. So if the photons, let's say, had the energy E0, then if I just multiply by h on both sides, I can say that if this is E0, this then will become the energy, the blue shifted energy. And so we can just replace that, and look, we now have the energy of the blue shifted photon. Whoa. But at this point, we might ask Einstein, but Einstein, is only half work done. We have another red shifted photon to calculate. And Einstein says, buddy, you've done all the work. You don't have to do any more work. How? Because if you look carefully, the only difference for the red shifted photon is that all the 5 waves are now in a distance of c plus v. So 5 waves will occupy a c plus v distance, and therefore you'll get a c plus v here, c plus v here, C plus V here. This means I immediately know that the energy of the redshifted photon must be the same as this, except there must be a C plus V in the denominator. We've done it. We've figured out the Doppler shifted energies, relativistic Doppler shifted energies of the photons, and we're now ready to plug this in. Now, sometimes when I'm doing heavy math, I might forget the big picture. So Einstein reminds us, what are we doing again? Well, remember, our goal is to calculate the energy of the photons from the moving frame, and from that subtract the energy of the photons from the rest frame. The energy of the photons from the moving frame is basically adding these two. That is the total energy from the moving frame, right? And so now we just have to add them and simplify, which is do some amount of algebra. And so there's nothing to commentate over there. And therefore, I'll just play this on autoplay, leave the room, put some soothing background music for you to watch, okay? What happened? It stopped? Why did it stop? Oh yeah. Now we have 1 divided by 1 minus v square over c square. Remember, if we had a root over here, then this term would be gamma. But since there is no root over here, that means 1 divided by this number is gamma squared. That means this is basically gamma squared. And so you have a gamma squared and a gamma, so that cancels out. And so you get the total energy, the blue shifted and the red shifted photons total energy equals 2 times the energy of the individual photon, initial energy for the photon from the rest frame, into gamma. But what is this? This is the total energy from the moving frame. And that equals, what is 2 times E naught? Hey, E naught was the energy of the photons in the rest frame. That means 2 times E naught is the total energy in the rest frame. So this is the total energy in the rest frame. And look, the moving energy of the photons in the moving frame just happens to be the energy in the rest frame multiplied by gamma. And look, mathematically, we said earlier that regardless of what speed at which you are going with, it doesn't matter. You will always find this energy to be bigger than this rest. And you can now see it is bigger by the factor gamma, which is so wholesome and so nice. You can also see why this only happens at very high speeds, because gamma is almost 1 at very low speeds. So in Newtonian mechanics, this wouldn't work. Again, mathematically, we get the same result. Beautiful, isn't it? Now, all we need to do is plug this equation in over here and just equate. This is the last step, folks. By the way, at this point, if you want to try doing this yourself, it would be a great idea, because historic moment. You would want to have done this, tried this, deriving equals mc square yourself. I mean, this is such an amazing moment. All right, here's the climax of a few more algebra and we'll be done. Here goes. So if we substitute, the energy from the moving frame is E times rest times gamma minus this equals half delta mv squared. And so if we take E of rest common, we'll get gamma times 1 inside the bracket. And gamma is basically, remember, it is 1 over root of 1 minus v squared over c squared, but I can write that as 1 minus v squared over c squared to the power minus half. All right, how do we go forward? Einstein, how do we simplify this? Well, at this point, Einstein says, let's make an assumption. Let's assume that the speed of our rocket is not very high. So this v squared over c squared is a very tiny number. Now, if we assume it to be 0, then we'll get everything to be 0. So I can't make that approximation, but I have to make some approximation. So how do I do that? For that, the last step is to make a binomial expansion. Now, again, at this point, I thought like, oh my God, binomial expansion. I forgot my binomial expansion. But Einstein reminds us, well, you know what? You don't have to even remember binomial expansion. Even that can be done logically. A little bit of math. And to do that, Einstein asks, what is 1 minus x squared? Well, we know it's 1 minus 2x plus x squared. What is 1 minus x cubed? Well, minus 3x plus 3x squared minus x cubed, we know that. But if you look carefully, you see when you do raised to the power 2, your second term is 1 minus 2x. If you raise to the power 3, your second term becomes 1 minus 3x. Therefore, what is 1 minus x to the power minus half? Just from this, we could say it's going to be 1 minus that same number times x plus some other number times x squared plus something times x cubed and so on and so forth. Now, if our x is much smaller than 1, like in the case over here, because v is much smaller than c. So if x is much smaller than 1, then x squared becomes even smaller. And so the way we do the approximation is we could say, hey, let's not worry about all the higher powers of x. And therefore, we say that if x is much smaller than 1, then this number is approximately equal to 1 minus half of x, or that is basically 1 plus x. 1 plus half x. And so that's the approximation that we can do. We call this the first order approximation. And so if you just plug this in now, this is x, so it'll be 1 plus, so let's just plug this in. What will we get? We'll get 1 plus half times v squared over c squared minus 1. We're almost done, folks. We just now have to do a little bit of algebra. The 1 cancels out. The half cancels out. Look at what we get. The v squared cancels out. Oh, here we go. Here we go. What do we get? There we have it. The mass that is lost must exactly equal the energy that was lost from the photon in the terms of photons divided by c squared. Right in front of your eyes, folks, we have derived E equals mc squared. So in summary, we first look at an atom which loses energy as 2 photons, jump into our friend's rocket and write down its energy. But our friend saw the same atom moving. Since moving sources produce Doppler shift, she sees the atom lose slightly higher energy to photons. The only way to solve the discrepancy is to admit that the atom lost some mass. And by computing the relativistic Doppler effect and plugging in, we find that the mass lost is exactly the energy of the photons in the rest frame divided by c squared. I hope you had a great intuition and the video lived up to its promise. So if it did, let me know. I'll see you soon.